Okay, so let's start. Hi, everyone, and welcome to the second Zero Knowledge session. The first talk is going to be given by Yunton Zhang about efficient sum check protocols.
Thank you for the introduction. Hi, everyone. Good morning. I'm Yunton Zhang from Shanghai Jiao Tong University. Today, I'm glad to be here to present our new work on lookup arguments. First thing, what is a lookup argument? Protocol that involves two parties, the prover and the verifier. Where the prover has two vectors, which we call the subvector and the table, respectively. And the verifier has the commitment to these vectors. And the task of the prover is to convince the verifier that all the elements from the subvector appears in the table. And after some interactions, the verifier decides to accept or reject. The lookup arguments have been largely motivated by the recent development in Zk snarks, and it is particularly useful in proving the computations that involve a lot of bitwise operations. In traditional snark, bitwise operations must be represented by arithmetic gates, which can be very expensive, and lookup arguments can transform these bitwise operations into a lookup operation, into a big table, which can be much cheaper than the arithmetic simulation. So, lookup arguments, we are interested in a particular branch of research on lookup arguments that constructs based on the KZG polynomial commitment scheme. And this sequence of works focus on making the prover the prover costs independent of the table size. So this class of lookup arguments can work with very huge tables, such that the tables can be used to encode operations that have very wide input. And the state of the art of this sequence of work is ZQ Plus, which was just presented yesterday at this conference by Antonio. And our work is concurrent work of ZQ Plus, and both of our works follow-up works on ZQ and try to improve the efficiency of ZQ. In detail, this work presents two protocols. First is LOSUM, a new universality sum check based on the KZG polynomial commitments. And then based on LOSUM, we present a new lookup argument called log. First, we will introduce the new universality sum check. So the protocol involves a polynomial fx, in which for which the prover has the content and the verifier has the commitments, and the parties both share a domain. They agree on a domain, and then the job of the prover is to take every element from the domain and evaluate the polynomial at this point, then take all the evaluations and sum them together. And the prover is trying to convince the verifier that the sum is some target value S. Our idea to this problem is the following simple observation. So we first focus on the simple case, where the target sum is just 0. And the non-zero case can be derived from the zero case very easily. So in the zero case, consider all the polynomials, the set of all the polynomials that satisfy our requirements of the sum check. It's easy to find out that all these polynomials, they form a linear space. So the sum check is actually equivalent to a linear space membership check. And then, as we all know, every linear space have the basis. We can always find a basis for this linear space. So, given the basis, the membership is actually equivalent to that fx can be represented as a linear combination of the basis polynomials. And this new equivalent statements can be easily checked by an old technique that has been extensively used in some early age snarks like GOR16. The idea is to secretly sample random alpha in the setup stage, multiply this alpha to every basis polynomial, and produce the commitments to these basis polynomials after multiplied by alpha. We call this polynomial the alpha polynomial. And to prove that fx is indeed the linear combination of these basis polynomials, the prover simply generates the commitment to alpha multiply fx. Intuitively, it is computationally infeasible to generate new commitments to new alpha polynomials, except by linearly combining the existing ones. This is known as knowledge of exponent assumption. So, given this commitment to alpha times x, the verifier can easily check the correctness of this proof by a single pairing. And just multiply fx by alpha. So all about this protocol, except one last thing. That is, how do we choose a basis? Theoretically, every basis can work with our protocol, but we want to choose one that can make the approval most efficient. So that actually depends on how the prover stores the polynomial internally in its memory. And in most cases, or for most snarks, the polynomial is stored by its evaluation form. That is, the prover stores the evaluations of this polynomial on every point in the domain. So in that case, we can easily find a basis such that the evaluation values are exactly the coefficients. So the prover does not pay any additional cost to compute the linear coefficients. Okay, that's all for this new univariate sum tag. Next, we'll use this as a building block to construct this our new lookup arguments. And as I said before, this construction is based on the CQ scheme. So let me briefly recall the core idea of CQ. So we start from a subvector and a table. Then the subvector is represented by a polynomial fx evaluated over domain D. We call it the smaller domain. And then we have this table represented as the evaluations of another polynomial tx over a larger domain. And because we assume that the table is much larger than the subvector. And we also, without lots of generality, we can also assume that D is a subset of H. And now for simplicity, I will just refer them as a smaller polynomial, smaller domain, and the bigger domain and bigger polynomial. And now the job is to prove that the evaluations of the small polynomial is a subset of the evaluations of the bigger polynomial. And now we apply this famous logarithmic derivative technique that is proposed by Habok in his MV lookup paper, that transforms this subset relation into the equality of two fractional functions. And then we check the equality as a randomly sampled beta. And finally, this problem is transformed into checking the equality between the sums of two polynomials, respectively evaluated at the two domains. Okay, that's basically the idea of CQ. Next, we optimize CQ as follows. First, optimization, which is also achieved by CQ plus, that is to merge the two sum checks into one. Of course, we use different approach to achieve this optimization. In our work, we first observe that the reason why CQ uses two sum checks is that the two polynomials are respectively summed over two different domains. So the natural idea is to unify the some domain. So idea is to redefine. We change the definition of the GX here. It was originally defined as an interpolation over a smaller domain. Now we extend the definition and additionally require that it evaluates to 0 over the larger domain, such that the sum of the larger domain is still the same as the smaller domain. And after this redefinition, we can see that this smaller polynomial now becomes a bigger polynomial. And of course, this will introduce some challenge, for which I will explain later how we overcome the challenge. And the second optimization is just to apply our new sum check to this unified one single sum check. Here is a step-by-step introduction explanation of our protocol. So the prover has input the 2 polynomials, and the verifier has the commitment to these 2 polynomials. And the start of the protocol is the same as in CQ. The prover prepares the counting polynomial mx that encodes how many times each table entry appears in the subvector, and sends the commitment to this polynomial to the verifier, and it receives the challenge beta from the verifier. So that's the same as CQ. And next, the prover computes the 2 polynomials as defined before and sends their commitments to the verifier. This is also similar to CQ, except that here the definition of GX has been changed. Next, we have 2 tasks. The prover has 3 tasks. First, prove the correctness of the 2 committed polynomials, and then prove that the 2 polynomials have the same sum. So we first deal with the third task. That is accomplished using our new univariate sum check, obviously. And I will not explain the details because I just remark that computing this sum still just requires the number of scalar multiplications that is independent of the table size because of the sparsity of the polynomial representation. And the univariate sum check is also adapted according to the context. And then the challenging part is to prove the correctness of GX and WX here, because the definitions of these polynomials involve the bigger domain. And without diving into much details, I will only summarize that the challenge here is to generate the polynomial commitment to these 2 quotient polynomials, Q1x and Q2x, and the prover need to finish to do this in time that is independent of the table size, that is the size of the bigger domain. And however, here the 2 polynomials in the definitions involve polynomials of the bigger size. So that's a challenge. And for Q2x, here everything is the same as in CQ. We use a technique called cache quotients, which I will not explain in detail here, but everything is just the same as in CQ. In fact, quotient is just where the name of CQ come from. And for this Q1x, we know that although in the definition, we have a lot of polynomials that have the size of the table, but we can actually rewrite this definition such that the denominator and the numerator are both polynomials of a size of the smaller size. So that the prover can compute the coefficients of Q1x in time that is also independent of the table size. And finally, the prover linearly combine the 2 quotient polynomials using the challenge sent from the verifier, and since just one polynomial commitment to the verifier. Note that this is also possible because we have merged the 2 sum checks and everything is happening on the same domain instead of 2 different domains. So that's the end of the interaction. And finally, the verifier checks first the sum check using one parent check, and then checks the correctness of the two polynomial commitments and the quotient polynomial sent from the prover that has also had been linearly combined by the random challenge zeta here. And then also note that in the two pairing checks, we have both we have WX commitments appearing both here and in the second. And checking in the second check, and so is the same is for the GX commitment. It also appears twice. So we can further merge the two pairing checks by another linear combination, and to save another pairing check. So finally, here is the comparison between our work and the whole sequence of lookup arguments, and we also estimate the proof size using instantiating the group the pairing with the BLS 38112 group. And here are the results. The proof size is so far the smallest among this sequence of works, and so we have also managed to cut the verification cost to 4 pairings. And the proving cost is also on the same level as the previous works. And finally, about the zero knowledge, note that our work is the only one that has just group elements, but not field elements in the proof. That is something similar to growth 16. This makes it's very easy to randomize our proof, such that adding the zero knowledge does not incur any additional costs. In fact, we also achieve full zero knowledge, which was defined in the CQ Plus paper. Okay, that's all for my talk. Thanks for listening.
Thanks a lot. Very nice presentation. Does anyone have any questions? Yes, please.
So, like, since you are now introducing this alpha in the
Yes.
CRS, is your CRS upgradable or not anymore?
I haven't investigated whether it is updatable, but it is still kind of universal because it only depends on this setup. At least it only depends on the basis polynomials, which only depends on the domain. And at least it does not depend on the table. So that's still some level of universality here. But I haven't analyzed if it is updatable yet. It's maybe future work.
I have a quick one. So basically, sometimes we need to perform lookups where we don't just check like whether the evaluations of one polynomial belong to like the evaluations of another one. Sometimes we need to do things that are a bit more complicated, where we check like collection of polynomials and another collection of polynomials. Do you know if your protocol will be able to handle such cases or be easily extended to some cases?
So in the table case, several columns table and subsets of another table.
Yeah. I think like the polynomials are completely different. So you're checking like let's say some polynomial one, and then like at the same time on the table that you're checking inclusion, you're checking some another polynomial and some other polynomial. So
I didn't quite get the situation that you described.
I don't know exactly what the table condition here is. Yeah, maybe you should right? Because that is okay, I think this is it. Let's move on to the next talk. Thanks a lot. Let's speak again. So, perfect. It's Well, I think we're ready for our next talk, which is given by Bhumika about the comparison of protocols. Please go ahead.
Thank you for the introduction. Hi. People from the back. Hi, I'm Momita Atta, currently pursuing my PhD under the guidance of Dr. Chaya Ganesh and Dr. Arpita Patra. Today, I'll be discussing our work titled Succinct Verification of Compressed Sigma Protocols in the Updatable SRS Setting. This is a joint work with my advisor, Dr. Chaya Ganesh, and another fellow PhD student, Neha Jawarkar. First, let us start with the question, what are zero-knowledge proof of knowledge? Here, we consider two designated parties, one prover and another verifier. And the prover wants to convince the verifier that it holds a witness to a public statement. However, to do that, it is reluctant to reveal the witness. So instead, it interacts with the verifier, and at the end of the interaction, the verifier outputs whether it accepts or rejects the claim. This can be used in instances where, for example, the prover wants to prove that it knows three coloring of a graph, but it does not want to reveal the three coloring itself. At the end of the interaction, which we call a protocol, we want the following guarantees. We want completeness, that if a prover holds a witness, it should be able to convince the verifier. We want soundness, where a corrupt prover which does not hold a witness should not be able to convince the verifier of a false statement, a false claim. And specifically for proof of knowledge, we want stronger guarantees than just soundness. We want knowledge soundness. That is, when let us consider the case that the prover is able to convince the verifier. We say that there exists an efficient extractor algorithm that can output the witness, that can extract the witness from the prover's head, if it is able to convince the verifier. Additionally, we want guarantees of zero knowledge, where basically we want that the corrupt verifier does not learn anything beyond the fact that the prover holds a witness. It should not learn anything beyond the validity of the claim. Here, zero-knowledge proofs are often deployed in settings like blockchains, where one person, a very powerful entity, will just compute the proof of update. So basically, you update the block, and then you provide a proof of correct update. Now, these are usually tech giants which have large computation powers, and the people who are verifying the updates are people like us with limited computation powers. So basically, we want the verifier's work to be much lesser. And we want the following guarantees. We want proof succinctness because the verifier has to read the proof. And we also want verifier succinctness, where we want the computation done by the verifier to read the proof and then do whatever computation is required to validate the proof should be less. Now, for settings like blockchain, as we discussed, right? We cannot exactly expect the prover to interact with everyone present for convincing everyone of the claim. For example, it can just post a correct update and everyone should be able to verify at its own leisure. So in such cases, we want the proofs to be given at one shot. Now, even for delegation of computation, we can use non-interactive zero-knowledge proofs, where you want a powerful but untrusted server to compute the large computation on your behalf. This is a stronger notion, so we need stronger assumptions to facilitate this. So we assume a setup at the onset of the protocol between the prover and the verifier. Let us talk about the setup. The setup can be based on a random oracle model, where basically the prover and the verifier gets an oracle access to a random function. Here we consider public coin protocols, so where we actually consider the verifier to only toss random coins, and then it also sends the randomness across to the prover. Also, we have setup based on CRS, which is common reference string, which, I'm sorry, is there any question? Oh, sorry. Setup can be based on common reference string as well. We'll take a closer look into that. CRS-based setup can be transparent or trusted. Transparent setup, CRS setup, usually talks about truly random coins being sampled and is available to both the prover and the verifier. And in trusted setup, the soundness guarantees holds only when you keep the randomness hidden. So if you do not keep the randomness hidden, your soundness is broken. note that the soundness guarantees we are talking about is with respect to a correct prover who is trying to convince the verifier of a false claim. As a middle ground, we have updatable setup. It has more structure to it, which is unlike transparent setup. And unlike trusted setup, we do not rely on one trusted framework. It is with respect to many updates to a CRS. And as long as one honest update is made, you trust that it is correct. We'll take a closer look into that. So let's say you have CRS1, which is a common reference string, and then you want to update it to another common reference string, say CRS2. For that update, you can contribute randomness to CRS1 to get to CRS2. And similarly, that contributing of randomness can be done many times. And then you get a final CRS after the nth update. And we call this the final CRS, which can be used in the protocol. Now the question is, how do we ensure that this CRS is usable? As we discussed, as long as one honest update is made, it should be usable. So let's say the second party is honest and we have green randomness there. So it should be, we are able to use this in the protocol to retain all the soundness guarantees. Now the question is, how do we ensure that there has been made an honest update? For that, we can always, if you do not trust whatever has been done before, you can always make the final update and just use the updated CRS for your own protocol. Let's talk about Sigma protocols, which are a nice class of proof of knowledge protocols. These are 3-round public coin knowledge sound protocols. So these basically goes like this. The prover sends a commitment to the randomness it is going to use in the protocol. The verifier samples the challenge, making it a public coin protocol, and sends it across to the prover. The prover then responds with another message. And at the end of this interaction, we have these guarantees. We have a linear proof size protocol and linear verification complexity. Now, Ataman-Kramer's work lifts these Sigma protocols to logarithmic proof size. However, it retains the linear verification complexity. Our work asks the question, can we make it verifier succinct along with having the proof succinctness? So let us first take a look at the Sigma protocol. Usually the large responses are the first message and the last message. But the first message is easier to compress, so we will not go into that. We'll take a look at the last message. And Ataman-Kramer's main observation is that you do not need to send it across. This is actually the bottleneck for linear communication, and you do not need to send it across. Instead, you can give a proof of knowledge. But you need to make sure that it is a compressing proof of knowledge. You cannot give a same amount of data in the proof of knowledge and expect it to be succinct. Now the question is, how do we compress it? Because this is also proof of knowledge, what we saw before, Sigma protocol, but we want a compressing proof of knowledge instead. So they use split and fold technique. You just split the vector into two parts, and then you take a random linear combination using the verifier's challenge, C prime. So this is how the last message of the compressing proof of knowledge is found. And of course, if you send this across, it will again make the verifier linear because that is n/2 length response. So you will again go through the whole process of doing a compressing proof of knowledge instead. This compressing proof of knowledge will retain the guarantees provided by the Sigma protocol, but it will ensure that your proof size is getting shorter and shorter. Use this recursively. However, instead of these compressing proof of knowledge, the public parameters also goes through same updates. It also goes through the split and fold update that we discussed earlier. And this is the main bottleneck, which we consider in Ataman-Kramer's work. So we want to go from linear verification to logarithmic verification. And we identify that the key piece of information which makes the verifier linear is making the public parameters update. So the first step to ensure that the verifier has to do less work, we can always delegate the computation of the public parameters to the verifier, to the prover. And the verifier can just check the correctness of the updated public parameter. And second, we should also ensure that the public parameters do not contain any linear length elements, because of course the verifier has to read the public parameters. Let us discuss the step 1. Okay, so as we saw earlier, right, we have an n/2 length vector being sent across if we just look at the first compressing proof of knowledge. So the public parameters also goes through the same process. So we have n/2 length public parameter being computed, and we want to delegate this computation to the verifier, to the prover for the verifier. So the key observation we make is that split and fold updates are easier to verify when we use structured commitment keys. Let's look at this structure where we say that the right half of the key is a constant multiple of the left half. So a key of length 2 would look like this, and a key of length 4 would look like this, where we just take the key of length 2 and add additional randomness to make it the right half of the key of length 4. Similarly, we do the same for getting the key of length 8. We go through this process, and this is how we get a multilinear key, and this is how it is defined. This is the key structure that we use for the structured commitment key. So we just need that the right half is a multiple of the left half. And why do we have this nice structure coming up? Because when we have these commitments that we need to compute, right, we can always only provide you commitment with respect to the left half, and we do not need to worry about what happens with respect to the right half. We have nice structure with respect to the left half. So let's say we want to compute commitments with respect to the key K, you have this nice commitment with respect to the left half itself. And once you send it across, you can always verify that the left half commitments are sent correctly by computing this. Verifier can compute this with respect to whatever has been sent across. And the split and fold techniques also takes a nicer form, which is easier to verify. So you can always delegate the computation to the prover, and the work that has to be done by the verifier is much lesser. Now let us take a look at the second step. The public parameters should not contain any order n-length elements. For that, pretty simple. We provide commitments instead. And since the public parameters also goes through the same split and fold updates, we use the same techniques that we saw before to just ensure that those updates are fine. So whatever we have seen before is with respect to opening of linear forms, which is a variant of inner product relation. So this is the relation that we where we use these techniques to provide a verifier succinct protocol. With respect to the state of art, we improve, for example, with respect to Daza et al., we improve over proof size and verifier complexity. And with respect to Dory, we improve over assumption and prover complexity. Similar results can be seen when we are talking about circuit satisfiability, which uses the linear form opening protocol along with other primitives to obtain the circuit satisfiability protocol. To conclude, we discuss how to get verifier succinct compressing protocols, which retains the proof succinctness obtained in the compressing protocol by Atama and Kramer's work. To do that, we first take a look at how to obtain verifier succinct linear form opening protocols, and which is a variant of inner product relation. And using that along with other primitives, we see how to get verifier succinct arithmetic circuit satisfiability protocols. And then linear form opening protocols to opening of group homomorphisms as well, when by ensuring that the assumptions that we are using also holds for structured commitment keys. So this is one thing that you have to ensure when you're using these techniques for structured keys as well. Please take a look at our paper if you have want to go through more details. It is available on ePrint, and feel free to reach out to me. Thank you. Happy to take questions.
last remark. So do you have questions?
Don't get why, how do your result can be applied to the updatable needs? I mean, in the first slides, you mentioned the updatable setting, right?
Yes,
How to update the CIs.
yes,
But I don't see how your result, your
Yes.
construction can be applied here.
yes. So first you have the setup phase where you get the updates. You do the updates and you get the CRS, and then you start the protocol. So you have this nice structured key with as a part of the CRS, which is obtained via the updates. And then once you ensure that, okay, you are fine with the updates, at least one honest update is made, so the CRS is usable, and then you go ahead with the protocol, and you have that nice structured key, which with respect to which you can then prove the entire.
So you mean your construction can work in that setting?
Yes.
I mean, your construction, your protocol can work in the updatable setting.
Yes.
Good, thank you.
Do we have other questions?
Yes.
Not sure how this question that you're working on the compressed sigma CSP problem related to the recent like staking sigma protocols.
Okay. So stacking sigma protocols.
It's like a group of
Yes.
instructions that can be compressed.
Yes.
Is it different from this one?
So our framework also essentially gives you a Sigma protocol itself. I think you can update the keys, and then when you update the keys and use just our protocol for that that CRS, I think it should be able to, it should be easy to get. I mean, not very easy, but I think you should be able to get the stacking Sigma working for that as well, because I think stacking Sigma already works with compressed Sigma protocols, so it should be working with our protocols as well.
Yes, it's like this. Since the sigma protocols can be staking, it's like looks like a compressed to me.
So the verifiers work is still linear. So even if you stack them, the verifiers work, if it is linear in one protocol, it will always be linear, even if you stack multiple things across, like you are having multiple protocols, you are stacking them together, but you are still having those multiple protocols. So it will always have the communication complexity of at least one protocol. And the communication complexity of at least one protocol, the proof size is succinct in CSP, but the verifier complexity is retained. I mean, linear verification complexity is still there. So it will still be. Yes.
How efficient would be to verify an update of the CLS? So you update the CLS,
Yes.
and then maybe the next party wants to see that you actually updated it, you didn't just CLS.
Okay. I believe it is efficient, but I am not very sure how efficient. So maybe I can take a look and get back to you later. Yes.
Okay, perfect. I think we have thanks a lot. With that, let's keep it together.
Right.
Okay. Just wanted to see if like to make sure that Zoom is actually working again, like we're not muted or something. Sorry, please. Second screen.
Okay, let's start our next talk, which is going to be given by Bogdan Ursu, and Sigma protocols and platforms. Yes.
Yeah, thank you very much for the introduction. So my name is Claudia Bartoli, and today I'll be presenting this work entitled On Sigma Protocols and Packed Black Box Secret Sharing Schemes, which is joint work with Ignacio Casigudo, who's my PhD supervisor. So let me start by briefly introducing Sigma protocols, very briefly, in particular after the previous talk. But these are free-run protocols in which a prover wants to convince a verifier that she knows some secret without revealing any information about the secret. So in particular, in this work, we are considering the case in which the secrets are preimages of homomorphisms. And these protocols must satisfy 3 properties that are completeness, case special soundness, and honest verified zero knowledge. So a classic example of Sigma protocol is the Schnorr protocol, in which a prover wants to convince a verifier that she knows the discrete log of some known value h. And so in the first message, what she does is that she commits to some randomness, then the second message is some challenge, and the last message is a linear combination between the secret and the challenge and the randomness. So this protocol satisfies the 3 properties, and in particular has 2 special sounds. And this property is given by the fact that given any 2 different valid conversations for which the first message is the same, the witness can always be extracted. And this extraction is made by the fact that we can divide C minus C primes, which are the challenges. So this extraction property relies on the fact that we are working over groups of prime order, and in particular, the challenges are in a field. So everything is invertible, right? So the question now is, how can we get to special soundness if now we're not in this case? So for instance, let's say that we are working over a group that has not prime order, or for which even the order is unknown. So this is kind of the motivation for our work. And what we do in this work is we present a construction of a Sigma protocol that can prove several pre-images of homomorphisms that can define over any abelian group, obliviously to the structure. So even for groups of unknown order. And we do this by considering the description of Sigma protocols through linear secret sharing schemes. That is quite natural, and I'll explain in a second. But first, let me just briefly recall what linear secret sharing schemes are. So are these schemes for which some secrets can be distributed among, let's say, n participants that satisfy T privacy and R reconstruction. So T privacy in the sense that if any T or less participants get together, they learn no information about the secrets. However, if R or more participants put together the secrets, their shares, they always are able to reconstruct the secrets. So in particular, for the case of linear secret sharing schemes, the shares are given by the multiplication of some matrix that usually is called the generator matrix times the secrets and some randomness. So let's see how this implies a Sigma protocol. So because we are considering a linear secret sharing scheme, which generator matrix is M. Let's say that for participant I, the share sigma I is given by Mi, that are the rows generating this particular share, right? So now the Sigma protocol is the following. The first message is kind of the same as in a normal Sigma protocol, where the prover is committed to some randomness. And now the challenge can be seen as a random selection between the participants. So let's say that selects participant I, sends this challenge, and now the last message is the share corresponding to that participant, for which the prover uses the randomness that committed to before. So this Sigma protocol satisfies the 3 main properties as completeness, because F is an homomorphism and the secret sharing scheme is linear. Has R special soundness, because, well, in this case, for simplicity, we're considering the case of having 1 privacy and R reconstruction. So given any R different conversation, this implies having R different shares, so the secrets can be reconstructed, so can be extracted from the Sigma protocol. And the soundness error of R minus over N. So in particular, we are interested in the case of secret sharing schemes that have a large number of participants, so that the soundness error is small. Plus has honest verified zero knowledge because of the privacy property of the secret sharing scheme. Moreover, the complexity of the Sigma protocol is determined by the share size of the secret sharing scheme, right? Because of the last message. So let's recap what are the properties from the secret sharing scheme that we want in order to have this efficient Sigma protocol. So first, we want the secret sharing scheme to be linear so that we have correctness. We want it to have 1 privacy and 2 reconstruction, so that we have 2 special soundness. We want to have a large number of participants, because as I mentioned before, that implies having a small soundness error. We would like to have a small share size so that the communication is efficient. And finally, we want this to be able to work over any abelian group. So this last point leads us to the usage of black box secret sharing schemes. There are these secret sharing schemes that were defined by Desmond and Frankel in 1994, and are basically linear secret sharing schemes that work over any abelian group. So that's great. And in particular, for these black box secret sharing schemes, we know that the minimum share size is log n, where n is the number of participants, even if we are only sharing one secret. And this is a result from Kramer and Fair 2002. So we would like to have a share size that is around log n. So these secret sharing schemes, how they work is if we consider n the number of participants, we'll have a family of matrices m1 to mn. So that for each participant I, the shares are going to be given by the matrix mi times the secrets plus some randomness. Right. So since we would like to have two reconstruction, what this implies is that given any two different matrices, the subtraction of them must have a pseudo inverse. And why is that? That's because then if we have two different shares and we subtract them, if we multiply them by the pseudo inverse, we can reconstruct the sequence. So now, because we want this to work over any abelian group, actually this pseudo inverse must exist over the integers, right? So we want that this pseudo inverse property works for the matrices defined over the integers. So let's see how we define such a family, how we construct it. So these are two examples of families that satisfy the pseudo inverse property. The first one is kind of trivial, and so the second one implies a sigma protocol of 4 participants because we have 4 families, and they share 2 secrets in the share size of 2 elements. So that would be like log n. And more interestingly, what we have is the case of 3 secrets for which we know that there exists this family of 8 matrices. And this implies a black box secret sharing scheme that has 1 privacy, 2 reconstruction, and shares 3 secrets among 8 participants. So that's 2 to 3 in 2 to 3 elements. So in 3 elements, right? So that would be log n, which is the minimum share size. So that's great. However, we don't know how to extend these constructions for larger case, because as I mentioned before, we would like to have black box secret sharing schemes that can share secrets for a large number of participants, between a large number of participants. So we have to use a different technique. And we base our technique in some implicit technique used in the work of Kramer and Bogdan in 2009. So the idea is the following. We'll consider the family that I explained before of capital N, in which we have 8 matrices for which we know that they satisfy the pseudo-inverse property. Now we extend the number of participants. Let's say we have N, which is A to the M for some natural number M. And now each participant I can be represented as a vector of size M in base 8. And this implies a one-to-one correspondence with a vector of matrices from the family capital N. So in this way, what we can construct for each participant I a bigger matrix Mi that has in the rows the matrices corresponding to its vector of the capital N, and then we scroll them to the right and we add zeros. So in this way, we now consider a different participant. Since this identification is unique, we can assume without lots of generalization that the first element is different, right? So if we now consider the matrix for participant J and we subtract these 2, what we get is that in the first diagonal, we have elements that are non-zero. And in particular, these elements are differences from the family capital N that satisfy the pseudo-inverse property. And that's why we can say that the bigger family of matrices M1 to Mn also satisfies the property of the pseudo-inverse. Anyway, of course, all the details of this process can be found in in the paper. So this kind of the idea. And what this implies is that there exists a black box secret sharing scheme with one privacy and two reconstruction that shares K secrets among N participants, for instance, 2 to the lambda participants, with a share size of K plus lambda minus 3. Right. So now if we apply this to the Sigma protocol, what we get is our main construction, which is a Sigma protocol that proves knowledge of K preimages of homomorphisms, that has two special soundness, a soundness error of 2 to the minus lambda, and a communication complexity of K plus lambda minus 3. Okay, so as I said, this is the main construction. Now let's see some of the application that it has. So the first application is class groups. This is a framework that was introduced by Castaños and Laguilamil in 2015 and can be thought as we are working in a group that is the product of another two groups, one for which is easy to compute the discrete log, and another one for which the order is unknown. So there are two homomorphisms for which we can apply our construction. The first one is the discrete log, and the other one is the proof of plain text knowledge. So in particular, for the case of the discrete log, what we have is that we actually, by applying our construction, we improve previous works. So compared to the first one, the work of Castaños et al. Presented in 2019, we improve the communication complexity, because what they do there is that they consider a binary challenge and they repeat the protocol lambda times in order to get a soundness error of 2 to the minus lambda. In the second work of Castaños et al. PKC 20, the communication in that case is a bit better than our case. However, they rely on some assumptions that in particular imply that the generator G is selected uniformly at random, which is not always the case in some applications. And moreover, in a more recent work of Brown et al. Crypto last year, again, the communication is a bit better than our case. However, they also rely on some assumptions, plus they don't get knowledge because in their application, they don't need to extract the secrets. So what we get in our work is that we have a communication complexity which is better than the first one. We get knowledge because we can extract the secrets, and we don't need extra assumptions. So just before I conclude, another application is the case of decay-ready functions. These are functions that were defined by Kramer and Damgard in their work of Crypto in 2009, and can be seen basically as functions that are almost homomorphic. So in our work, we explain how our Sigma protocol can be applied also in this scenario. And a particular example of decay-ready function is the Joly-Bert encryption scheme. It is given by this function over here. So for this, we could also apply a straightforward our Sigma protocol. However, in this specific case, we know how to improve the communication complexity. And this improvement is made by the fact that in this case, we can use the extensions to Galois rings. This is not something new. It has been already done, for instance, in the work of Atema et al. At TCC 2022. Yeah, however, as far as we know, for the specific case of the Joly-Bert has not been done before. And the communication complexity is K elements, because over these Galois rings here, we can use Shamir secret sharing schemes, and that's more or less a trick. So just to finalize some conclusions. So in this work, what we do is we formalize the description of Sigma protocols through linear secret sharing schemes for any secret sharing scheme. So I said for 1, 2, and N, but actually it's for any T privacy and reconstruction. And we also include the versions for non-interactive, that are non-interactive. Then we present this general construction of Sigma protocol that proves a knowledge of K images of homomorphisms over any abelian group, even for groups of unknown order. We show the applications to class groups, and we show that improves previous works. And finally, we present these extensions of this Sigma protocol to the case of ZK-ready functions, and in particular for the case of JVBERT, we improve the constructions using this extension to Galois rings. So that was it. Thank you very much.
So much. The presentation. Questions?
Can your technique be extended to handle more complicated relations, other than just showing your knowledge of the pre-image?
So the thing is, you need the fact that are homomorphisms in the complete property of the Sigma protocol. So as long as you guarantee that the verification of the like the check is works properly, then I guess you do. But in general, I would say no, depends, of course, on the statement.
For concrete example, how about the improve the equal x and the edge to x, the two elements have the same x. But can you technique do this?
Yeah, that's no, an homomorphism, or
Maybe we can check.
yeah, I mean, yeah, as long as the function like works when multiply the matrix of the black box solution scheme. So that's what you have to check.
Thank you.
If you increase R, then you get R special soundness. Does that work out favorably with the chatting space, or
Yeah,
just things too?
yeah, that's a good point. So you can work with that and play with it in order to have like different scenarios. However, since so affects usually the soundness error. So because it implies having like R-1, or even it also depends on how you choose the challenges to be. Because usually if you change the challenge just to be elements of size T, which is the privacy set, then you have, I think, R-1 over N. But if you choose different challenges, so maybe just elements that are more than T, then it gets more complicated. So the better soundness error that you can get is in the case of selecting challenges of size T, and then you get a soundness error of R-1 over N. But usually the most useful scenario is where you have two special soundness, so that you have just the size of the challenge set as like 1 over the size of the challenge soundness error. That makes sense.
So optimally when T is 1, R is 2.
Questions?
Your technique use a large space general proof, because the difference between the challenge in that space is not usually developable. So your techniques you use is large space structure.
Right.
If you can, what's the advantage of your techniques compared with this in other class-based techniques?
Yeah, so the question is about applying this to lattice space.
Yeah.
Okay. So we have not done it. However, we have an intuition because of the description of the matrices. Well, these matrices come from here, right? And these are all elements of 0 and 1s. So maybe because of that can be useful in some lattice space encryption scenarios. But however, we have not studied it, so I cannot say.
It's, maybe we have time for one more. Okay, let's conclude. Thanks a lot. Let's take the speaker again.
Unfortunately, the last talk is going to be a video because the speaker could not attend. I found it. Yes.
Yeah.
Hi, my name is Xindong Liu. Today I
Okay, so let's start. This is going to be a talk by Xindong Liu from the Institute of Information Engineering about short code-based one out of many proofs and applications.
Hi, my name is Xindong Liu. Today I will report on short code-based one out of many proofs and applications. My report is divided into the background, preliminaries, and our work.
If you can make
I will first
like louder or it's fine there. I don't for me it wasn't good. It was a bit weird.
introduce the background. One out of many proofs is a type of ZKP protocol in which, given a one-way function and a set containing n images, the prover proves that it has the pre-image of an image in the set. One out of many proofs have many application scenarios, such as serving as components of other primitives like ring signature scheme, group signature scheme, and group encryption. They can also be used to construct a confidential transaction protocol and blockchains. There are many ring group signature schemes from coding theory, and we list some representative schemes. For ring group signature schemes, there are linear size ring signature schemes, such as ELLNW15 and BGM21, and log size ring signature schemes, such as NDWZ19 and BBNPS22. There is no group signature scheme based on the code equivalence problem. In the following, we will introduce two hard problems in code-based cryptography: the SIGOM decoding problem and the general decoding problem. The definition of the SIGOM decoding problem is given a parity check metric H and SIGOM S. The SIGOM decoding problem is finding a vector E satisfying HE equals S and WE equals T. The definition of general decoding problem is given a metric G and a vector Y. The GSD general decoding problem is finding a pair of vectors X and E satisfying XG as E equals Y. Then we will introduce our work. Our work consists of constructing one out of many proofs, constructing ring signature scheme, and constructing group signature scheme. Our idea comes from a key observation about the Stern protocol. Stern protocol is a ZKP protocol for proving knowledge of the pre-image of a SIGOM. In the first round, the prover first sends three commitments, C1, C2, C3, to the verifier, who responds with a ternary challenge. If the challenge is 1, the prover opens C2 and C3 by sending pi, r, row 2, and row 3. And the verifier's verification procedure is independent of the SIGOM S. If the challenge is 2, the prover opens C1 and C3 by sending pi r as E, row 1 and row 3. And the verification procedure of C1 depends on S, while the verification procedure of C2 doesn't depend on S. If the challenge is 3, the prover opens C1 and C2 by sending RSP, and the very first verification procedure is independent of the CJOM S. We make a small modification to the Stern protocol, replacing the original commitment C1 equals HR pi rho 1 with HR as S P pi rho 1. C2 and C3 remain unchanged. The modified Stern protocol still has completeness, soundness, and zero knowledge. SD-based one-on-many proofs consists of parity check metric H and AC JOMs. The prover proves that it has a pre-image of some CJOM. The prover first generates n commitments. C11 equals HR as S1 pi B1 to CN1 equals HR as Sn pi Bn. Then shuffle these n commitments and compress them to a root using a Merkle tree. The randomness Bi is generated by a seed tree. The prover they replace C1 of the modified Stern protocol with root, while keeping C2 and C3 unchanged. This is inspired by the paper BKP 20. The prover returns a ternary challenge. If it returns 1, then the prover opens C2 and C3 by sending pi r as E, row 2 and row 3. If it returns 2, then the prover opens C1 and C3 by sending pi r as E, row 1, bg, and the path of Merkle tree. If it returns 3, then the prover opens C1 and C2 by sending pi r and seed. We can obtain a GSD-based one-of-many proof by applying similar ideas to the Verse framework, which has a lower communication complexity than SD-based one-of-many proofs. Ring signatures are a direct application of one-of-many proofs. We can get the corresponding ring signature scheme by doing an FS transform on the GSD-based one-of-many proofs. In our ring signature scheme, each user's public and private key is an instance of the GSD problem. We make a comparison. We compared with other ring signature scheme based on the SD problem or its variance. Our scheme has an advantage in signature length. Another application of our one-of-many proofs is group signatures. We use the encryption then proof framework to construct our group signature scheme. The framework consists of 3 layers, one of many proof for membership proofs, a variable encryption scheme for traceability, and a ZKP protocol that links the first 2 layers and ensures that the member honestly encrypted its own edits. To realize the second layer, that is proving that a ciphertext CT of the form McAlice encrypts some I in a set from 1 to n. We generate the following set using CT. Then we prove that some element in the set is an instance of the GSD problem. This is one out of many proof. Combining the one out of many proofs of the second lawyer with one out of many proof with the first lawyer results in the underlying protocol for a group signature scheme. Finally, we apply the Fiat-Shamir transform to it to obtain our group signature scheme. Compared with other code-based group signature scheme, our scheme has an advantage in signature length. This is our work. Thank you.
So thanks everyone for coming to the second journalism session.